Okay, welcome. This is the first homework. This is Structure and Properties of Matter, Homework 1. We will be covering physical properties of matter, states of matter, kinetic theory, chemical properties of matter, and Archimedes' principle. So, first section, physical properties of matter. Now, know that all of this material has been covered in class already. So, this is a review of the material that we've already discussed. So, physical properties. These are all substances have physical properties. For example, mass, density, volume, color, shape, smell, melting point, freezing point. These are all physical properties. And what is a physical property? So, a physical property is a characteristic that can be observed or measured without changing the substance. So, color, melting point, conductivity. These are all things that can be that won't change the substance when we're observing them. So, a physical change makes a change to the appearance. So, melting point, freezing point, when it changes, when something melts or something freezes, it's still the same substance. It's just changed its state of matter. Volume changes, it's just less of it. Shape change, it's just a different change. None of it changes the actual substance. So, regardless of the physical change in this particular picture here, it's still water. It can change states, it can change shape, it can change volume, but it's still water. So, what are the physical properties? Well, here they are. So, density, which is the amount of matter packed into a given volume. The more of matter that's packed in, the higher the density. Magnetism, the ability to attract or repel objects. Melting point, it's when goes from a substance goes from a solid to a liquid. Boiling point, when a liquid goes to a gas. Conductivity, how much heat or electricity move through the matter. Hardness, which is just the ability of a substance to be scratched. Luster, which is just the shininess of a substance. Malleability, we can flatten things into sheets. Um, Ductility is how you can pull it into a thin wire. Solubility, the ability of a substance to dissolve another substance. So, like dissolving salt in water. Now, mass is also a physical property. So it's just a measure of how much matter is in the object. Or volume, that's the amount of space that the matter takes up. Now, when we look at changing in states of matter, you can go from with melting point and boiling points. All right. You can look at the heating curve. All right. That's over there on the right. So when a solid heats up, now all of a sudden it will level off and it's still absorbing heat, but that heat is actually breaking the bonds so that it converts from a solid to a liquid. Okay. Then it absorbs more heat, more temperature goes up. All right. Until it hits that boiling point where it starts to boil. Well, it's absorbing more energy, but it's not getting any hotter until it converts into a gas. So the gas is when it's been fully converted, and now it's all vapor. It's no longer liquid. If you heat up a gas enough and you get enough pressure and enough heat, that gas will actually transform into plasmas. But we don't see plasmas here on Earth naturally. Those things only occur because of pressure and energy in the center of a star. So, what exactly is density? Well, density is calculated using mass divided by volume. So a substance with a higher density than another substance will have of equal volume will have a higher mass. So density is a size independent property, meaning that it does not change when it's the size of the object being measured changes. Mass, volume, weight change when size of that object change, but density doesn't. So if you take an object and you cut it in half, it still each half has the same density because you've now reduced the amount of mass and the amount of volume at the same time. Now, which one would be more dense, a gas or a solid? Well, a solid is more dense. All right, a solid has more matter packed inside of a given volume than a gas does. So, same size but different weight. All right, the higher density weighs more. All right, so if mass or volume changes without the other changing, all right, it will change the density. This can only happen when the surrounding pressure changes without it being a chemical change. All right. So, you've got, if you've got a volume stays the same, an increase in mass will increase the density. If the volume stays the same, a decrease in mass will decrease the density. We understand that, right? Now, and the other one's a little bit harder to understand if the mass is staying the same. If we lower the pressure and now all of a sudden the volume increases, well, the density goes down. That happens with gases. Now, if we have a higher pressure where we are condensing all of the molecules together, well, we're decreasing the volume, so we're increasing the density. So let's look at a density calculation. So what we're going to do here, calculate the density of an object that has a mass of 124 kilograms and a volume of 31 centimeters cubed. So we just simply take the mass from the problem and divide it by the volume. That gives us the density. All right. So D equals M divided by V. That's how we do it. That's the formula. So if we take the mass and the volume from the question, 124 kilograms divided by 31 centimeters cubed gives us, all right, gives us 4 kilograms per centimeter cubed. You can see that, guys, right? Awesome. Okay, now we're going to go on to states of matter and the kinetic theory. So let's go over them. First, there's the solids. So solids have the least amount of energy. They're closely packed together, particles. All right, everything is really, really packed together. They don't have enough energy that the particles can actually move past each other. They have a definitive shape and they have a definitive volume. That energy, though, it's so little that the particles can't slide past each other. The next state is liquid. All right. Liquids have more energy than a solid. All right. Particles can slide past each other. They still have a volume, but that volume will take the shape of the container that it's in. Those particles still move around because they have enough energy to actually slide past each other. But they do have this volume and they stay in a given volume. The third state, which has more energy than a liquid, that's a gas. All right. Particles can move past each other, collide with each other. The more energy, the more they collide. They have no fixed shape. They have no volume. All right. They take the shape and volume of the container that they are in. So the bigger the container, they spread out. If it's a small container, they're all tightly packed. Right? That means that it's more pressure to fit all that gas in a smaller container. Okay. And the fourth is a plasma. All right. Plasmas contain both positive and negative ions. All right. Positive ions and negative electrons, excuse me. Matter is not only enough energy to overcome the attraction between the particles, but now also has enough energy to break apart the atoms themselves. So now we can get some of those different atomic reactions, nuclear reactions, in the center where the plasma is. Now, coincidentally, most ordinary matter in the universe is in the plasma state. All right. That's because most matter is found in stars. So if you look at our solar system, like 98% of the matter in our solar system is in the sun. Okay. Only about 2% of the matter can be found throughout our solar system in the planets, moons, asteroids, meteors, etc. Now, when we compare all of them together, solid, liquid, gas, and plasma, this is how we would represent them. Okay. Solids on the left, you notice how they are tightly packed. Liquids next to it, to the right, and liquids are now spaced out a little bit, right? They're still kind of have, you know, a little bit, of a shape to it, but they're spaced out a little bit. Okay. Gases spaced out a whole lot more. And then finally, plasmas, now you have the positives and the negatives. So to go from a solid to a liquid, you're talking about melting. To go from a liquid to a gas, you're talking evaporation. To go from a gas to a plasma, you're called ionization. Now, if we go reverse, to go from a plasma to a gas, deionization. To go from a gas to a liquid, condensation. We know that from our water cycle. And to go from a liquid to a solid, we're talking about freezing. Now, if you notice, this is going from a solid to a liquid, liquid to a gas, gas to a plasma. That is the direction of increasing temperature, increasing heat, and increasing energy. If you go backwards from plasma to a gas to a liquid to a solid, that is decreasing temperature, decreasing heat, and decreasing energy. Now, this all revolves around the kinetic theory. So, all matter is made, the kinetic theory just states all matter is made of atoms that collide constantly with greater speed and space as their energy increases. So, more energy means that they are hitting each other more and they space out more. So the states of matter, all right? States of matter, when you go from a solid to a liquid, liquid to a gas, and those are the three states here on Earth, all right? You're talking about increasing in temperature. And that comes along with an increase in kinetic energy. The atoms themselves or molecules are moving around more. They are increasing in their particle motion. They're increasing volume because they're spreading out. Okay. Now, as temperature increases in a substance, those particles they space out more and more and more and move faster and faster and faster. That's how kinetic theory works. Okay, on to chemical properties of matter. So, what are chemical properties? Well, all substances have chemical properties. For example, flammability, oxidativeness, toxicity, radioactivity, light sensitivity, reactivity. These are all chemical properties. So, what is a chemical property? Well, it's a characteristic that when you change it, will change the identity of the substance. So, flammability, oxidativeness, radioactivity, these are all examples of properties that if you change them in a substance, that they will change the actual substance. So, what's a chemical change? Well, a chemical property of a substance, when it changes, that substance identity changes. So, when we take, say, for example, wood, if we burn wood, right, what do we end up with? We end up with ashes. Well, ashes is a different substance than wood itself. So after the chemical change, the substance is something new. So, what are the chemical properties? First one, flammability. All right, that's just the ability of a substance to catch fire. And certain substance will even ignite just by force and not even a spark or a flame. It's pretty cool. If you ever have some of these substances, we can show you how those will work. Oxidativeness is the ability of a substance to react with oxygen. The most common thing that we can think of is rust. So oxidation, though, occurs everywhere. So iron in the metal that oxidizes very easily, that's our most common one. But you can see this like oxidation on apples that have been cut open. You can even see it in rocks out in the western United States. Toxicity. So toxicity is a chemical property when that makes a substance harmful to living things. So, ordinary substances can chemically change into toxic chemicals, but some chemicals are already toxic to begin with. Radioactivity. So, this is the process of property of a substance that makes it more likely to release energy to make it an unstable nucleus. All right, more stable. So, what it's doing is it's actually getting rid of some of this energy, all right, so that it can make itself a more stable substance. Now, all state substances have radioactivity. Some simply have a lot more than others, and those are the ones that we consider radioactive, but all substances are. Light sensitivity, right? This is the property of a substance that causes it to change when exposed to light. So, newspapers, for example, newspapers, if you sit them out in the sun and they're exposed to light, they will turn yellow, right? It's the chemical that is in that paper, right? Paint is another substance that yellows over time, and when it's changed with exposed to the sun. You can look at just about anything that has any kind of color to it, and it will have a chemical change to it if it is exposed to light. Reactivity. Now, this is where the periodic table comes into play. The ability of a chemical substance to undergo a chemical reaction is determined by its position on the periodic table. So you can look at its position, all right, and it's influenced by the number of electrons of the reacting substances, all right, and it determines its ability to combine with things. So the most reactive metal is in the bottom left corner of the periodic table. And the least reactive element out there is in the top right. Okay. So we'll learn more about the periodic table later on in another unit. Now, chemical changes. First one, combustion. So this is when a substance burns. The resulting substance is a new substance. Like I said, when you burn wood, you get ashes, and ashes are not wood. Bubbling. All right. Bubblings can be a physical change, like with boiling water, which is a change in states, right? Change of state in states of matter, that's a physical change. But when a substance bubbles, it is usually releasing a gas that is formed by a chemical reaction. That is a chemical change. Unexpected color changes. An unexpected color change is when substances are mixed, indicating a new substance that has been created. When those two, it's just an unexpected kind of color change there. So there's something new. All right. Now, color changes can be physical. All right. But when it's unexpected, all right, from combining two chemicals, that's a chemical change. Temperature changes. So a temperature change means that energy is either being released or it's being absorbed, which indicates that there's a new substance being formed somehow, usually a gas. Now, exothermic reactions, those are releasing heat, right? Endothermic reactions are absorbing heat. Either way, both are a chemical change. Now, precipitates. Precipitates are pretty obvious, right? So when two substances combine, or there is a dramatic change in temperature for a substance, sometimes a precipitate is formed. Okay. Now, a precipitate is an insoluble substance that results from a chemical change. It's something that will not dissolve. It settles out to the bottom, like there in the picture to the right. Okay, on to Archimedes' principle. So, Archimedes' principle is fairly simple. It revolves around relative density. So, when we talk about relative density, we're generally talking about water, okay? And some substances only sink, some substances only float, and relative density has to do with the object's density versus the density of water, okay? So, an object's density relative to the water determines whether or not it's going to sink or float. So, if it's greater than one, it's going to sink. The object's going to sink. If the object's density is less than 1, it floats. And depending on how much less than 1 will determine how much it floats. So substances only partially sink. Substances that don't totally sink, the percentage of the substance below the top of the water equals the density of the substance. So 80% below the level of the top, all right, with just a little bit sticking out, all right, that means that the density is 0.80. So when we look at icebergs, for example, icebergs floating on in water, you see an iceberg on the top. You're only seeing a very small portion of what is down below the water, right? What's down below the water is the rest of the iceberg. Okay. Now, Archimedes' principle takes this into account. All right. So, Archimedes' principle is just the amount of water displacement by an object is equal to that object's volume. A rise of 10 milliliters equals a 10 centimeter cubed object volume. So 1 milliliter of water displaced by is displaced equal to 1 centimeter cubed of volume of that object. Now, this principle allows us as scientists to determine the volume of objects without knowing what the dimensions are. We can take a rock, for example. There's no way we can look at the length, the width, the height. We can't calculate the volume on it unless we use something like Archimedes' principle. And Archimedes' principle allows us to submerge the object in water, and the amount of rise in the water is equal to the volume of the object. So, how do we use this in the lab? All right. Well, to use this in the lab, what we're doing here is we are actually taking a graduated cylinder with a set amount of water in it. All right. Or another substance, usually water, though. We put the object in that water. All right. We know what the starting volume is. However much it rises, that is the volume of the object. Okay. So when any object of irregular shape is submerged, the increase in the volume of water is equal to the object's volume. Now, if we know what the length, the width, and the height is, if we can measure those things with like a ruler or a tape measure, then that's how we do the volume. All right. But if the object is not a normal shape, we can't get those lengths, widths, and heights. What we do is we submerge it into a liquid, and that gives us what this displacement is. And the displacement is equal to the volume of the object. Okay, good job. Finish up with your last questions.